Alright, so we're going to do section 2.2 now, in which we talk about function behavior. And what I mean by that are some basic function characteristics that allow us to distinguish one type of function from another. And there's lots of characteristics that we could look at. We're going to start with some very basic ones. But let's kind of warm up though first and remind ourselves what the graph of a function has to look like. So here's an example. This is a scatter plot, right? But is the scatter plot that of a function? Well, in order to be a function, it has to pass the vertical line test. So that just means we need to imagine that we have a vertical line that we can move through the entire graph, and if it ever intersects the graph in more than one location, then we are failing the vertical line test. So here, vertical line intersects once, here once again, and I can just kind of step through it because it's the scatter plot. I don't actually have a continuous interval to check, but it's pretty easy to see that we're not going to violate the VLT. So yes, this is a function. Okay. All right, so let's find its domain and range. Remember that when we're working with the scatter plot and we have discrete values, that our domain is going to be represented by curly brackets, and we have to list all the points. And so what I'm going to list here are the x coordinates of all these points. So this point is at -4. This one's at -2. Then the next one is that looks to be at 1. Then at 2. And then we have 5 and 7. So that will be my domain. Okay, for the range, that's going to be the y coordinates, and again, we'll need curly brackets. In this case, we want to start from the vertically lowest point and move up. So the y coordinate of this point here is 0. Then we go to 1. And both of these are at height 1, so I don't need to list that twice. This one is at height 2. And then we jump up to these two, which are at height 4. And there you go. There is our range and our domain. Let's look at a slide with the answers. All right. If we connect the dots, we haven't actually changed anything. It was a function before. It'll still be a function now because we don't have any points where we have one input with more than one output. So yes, this is still a function. The only changes to the domain and range now are that we are working with a continuous function. So instead of having curly brackets, in this case, I'm going to use a square bracket, and I'm just going to list the leftmost and the rightmost x coordinate. So for this one, that would be -4 up to 7. And that means everything between -4 and 7. Similarly for the range, we're going to begin bracket at 0 and end at 4. Okay, so that's just a warm-up to remind you how functions work in terms of their graphs and the definition of a function, and a little bit more about interval notation. All right, so let's now talk about some function behavior. This slide talks about what I would consider to be the 3 most basic types of function behavior: increasing functions, decreasing functions, and constant functions. Now keep in mind, we can mix these up. So you can have functions that are increasing and decreasing over different regions. So what do we mean exactly by this? Well, suppose we have a function y equals f of x. We say that f increases if its values increase. And when I say its values, I mean its outputs increase as x increases. So as the inputs increase. So the graph rises from left to right. Pictorially, this would be something like, let me get away from that color. Well, like this. As the inputs increase, the outputs increase. So what about a decreasing function? Well, the outputs will decrease as the inputs increase. So the graph will fall from left to right, and it will look something like that. Now I'm drawing pictures of lines, but that's not the only way that you can increase. You can also increase sort of in a curve, so you could have something like that, or something even like that, running out of room. Those are all increasing. Here's some decreasing ones. I could decrease like that. I could decrease like that, or I could decrease like that. Now a constant function, so this is one, oops, sorry. As I was saying, a constant function is one whose values don't change, and it has a horizontal graph. Now, the only way a function can be constant is if it's linear. At least, oops, I probably made that line a bit too thick. let me bring up my whiteboard. So constant would look like this. So here's my xy axis. If I have a function that's constant, it would do something like that. Now, I'm just indicating that it's constant over this interval here because, you know, I could have that it would start increasing over here. And I could have had that it was decreasing over here. So these can be mixed. All right, so another important point is how do you report this information? So if I ask you, if I give you a function and I say, where is it increasing, where is it decreasing, how do I expect you to tell me to answer that question? And so let's talk about that. Here's an example. So the question says, on what intervals is this function increasing, decreasing, and constant? What that means is x intervals. And this is always how this type of function behavior is reported, is in terms of the x interval. So it's easy enough to see just from the picture where it's increasing, decreasing, and constant, but you've got to make sure that you write it correctly. So let's go through here and just label this. So here we are decreasing, and that's the only portion. Here we are constant. Oh, and I just realized that I missed the decreasing, so I'll fix that in just a second. But so here I'm constant. Decreasing again. Increasing. And then constant. Okay? So we report this in terms of x intervals. So let's write this down. So the function is decreasing over 2 x intervals from here to here, which is -4 to -2. But then also here as well, and that looks to be from 1 to 2. So if you have two disconnected intervals, and we're considering them both, then we put a union sign between them. Okay. Where is the function constant? From -2 to 1, union 5 to 7. And where is the function increasing? There's only one region where it's increasing, and that is from 2 to 5. Okay. So here's your solutions. In slightly different order than I did them, but that's the those are your solutions. Okay. A natural thing to consider when you open the subject of increasing, decreasing, and constant functions is the related subject of turning points. And the reason why is because turning points are very intimately connected with increasing, constant, and decreasing functions. So what is a turning point? Well, it is a point where a function changes from increasing to decreasing, or from decreasing to increasing. So in other words, it's going to be something like this. Let me just draw a little sketch. Increasing to decreasing, there's a turning point. Here's another one. Decreasing to increasing, there's another turning point. Excuse me. Now, you can clearly see that although these are both turning points in the sense that we turn from one kind of behavior to another, there is something different between this and this. Namely, one is a high and the other one's a low. So as you can see down here, when we have an increasing to decreasing turning point, that's called a local maximum. And when you have a decreasing to increasing turning point, that is called a local minimum. The turning point itself is a point. Actually, let me bring up my whiteboard. Here's an example. Okay, let's actually name this point. Let's say that that's 4, 7. Therefore, the coordinates of this point are 4, 7. So the point 4, 7 is a local maximum turning point. Now, this whole thing about local, well, it's local because all we are claiming there is that it is the biggest point within the neighborhood. Okay, so local doesn't necessarily mean that it's the only turning point or it's the absolute maximum largest value of the function. It just means that it's the largest value kind of around here in this neighborhood. I can even like highlight that. So all around here, there's nothing bigger than 4, 7 for this function. So that means it's local. But if this function were to swoop back upwards and get higher again, then we'd have another local maximum. If you have a point that's bigger than any other maximum, that's called an absolute maximum, which we will talk about that later. Another point about this, or another thing to consider about this, is that 4, 7 has an x-coordinate and a y-coordinate, right? So the x-coordinate of 4, this is where the local max occurs, and 7 is the local max value. So what I'm doing is I'm drawing a distinction between the x-coordinate 4 and the y-coordinate 7. And there's a good reason for me doing that, because sometimes, especially in an application, we need to separate them.